Welcome back. What I'm going to do in this segment and maybe one or two more is almost take a step back and outline for you the main steps that are involved, the only slightly different steps that are involved in setting up two-dimensional problems. Okay, so we're following somewhat of a deductive approach where we go from the more general 3D structure of the problem to a 2D structure, which is, of course, just a particularization of 3D. Okay, we're going to do this in the context of the linear elliptic problem in 2 dimensions now with a scalar variable. Okay, so we will call this, of course, 2-dimensional linear elliptic PDEs in a scalar variable. All right, so since we're talking of linear elliptic PDEs with a scalar variable, the physical problems that this is applied to remain heat conduction and mass diffusion in 2 dimensions, right? That's all. Okay, there's actually very little to do, almost nothing to do, and I'm going to do just that, right? So here's my version of doing nothing. So I'm going to first, we'll start out with a strong form of the problem, and really all we have to observe is that everywhere in the 3D formulation where we observed that the spatial dimensions could, the spatial dimension index ran from 1 to 3. It now runs from 1 to 2. And we need to recall for ourselves how we would construct the basis functions from over 2-dimensional elements, right? Okay, so just for completeness, I'm going to put down fairly quickly the strong form and the weak form. Okay, and in fact, because I'm going to do that fairly quickly, let me straight away say that we're given the data. Okay, we're given UG, we are given J sub n, we are given F, and we are also given the constitutive relation minus ji, plus ji equals minus kappa ij u comma j, and here we have I comma j equals 1 and 2. Okay, this is what we're given. So with this background, here is the strong form. Okay, the strong form is find u such that minus j I comma I equals, now we'd used f in our first poser of the problem, and later on you will recall that I said that there was reason to replace that with a minus f bar. Okay, right, so this is our PDE, right, in omega. And we remember that now omega is it's a subset. Omega is a subset of R2. Okay, so the domain that we are looking at would be this. Right, but the difference that instead of drawing a 3-dimensional basis or 3 basis vectors here, I have just 2. E1, E2. Okay, so this is our PDE with boundary conditions U equals UG on what we understand to be the Dirichlet boundary. Okay, and minus J, sorry, I'm doing this all with coordinate notation. So minus Ji Ni equals J sub n for the influx condition on the Neumann boundary. And n now is a unit vector in 2 dimensions, right? Okay, that's it. That's our strong form of the problem, and I've already stated up here that I and j run over 1 and 2. Okay, I'll go ahead and write the weak form, and I will in fact write the finite dimensional weak form, right? Essentially skipping a step here. So I will write now the finite dimensional weak form. Okay, so that is find UH sub, sorry, there's no sub I here. Find UH belonging to SH subset of S, where SH consists of functions UH belonging to H1 over the 2-dimensional domain omega and satisfying the Dirichlet boundary condition. Okay, so find UH of this type such that for all WH belonging to VH subset of V, okay, where now VH consists of all weighting functions also to be picked from H1 functions and satisfying the homogeneous Dirichlet boundary condition. Okay, find UH such that for all WH of this type the following holds, right? Integral over omega WH comma I JH I. Now we are in 2 dimensions, right? So what we are working with here is an integral over an area, okay? So we get dA, right? So WH comma I JHI equals integral over omega WH F bar dA, okay? And what we note here is that, okay, that in order to get things right, we will pick up a minus sign there, okay? This is, I'm just working through all those changes I made with the signs later on in the 3D problem. Okay, so we have this plus integral over the Neumann boundary WH J sub n d. Okay, now we need to be a little careful here. In 2 dimensions, the boundary is a curve. Okay, so the boundary integral here I'm going to write as ds. All right, where for us s is now a curve. Okay, ds is the elemental curve. Okay, all right, so this is what we have. And the only thing we need to recall here is, as we did on the previous slide, just remember here that I equals 1, 2. Okay, and in this, of course, JHI we also know will eventually be written as kappa ij, minus kappa ij UH comma j. Okay, so j and I both run over 1 and 2. All right, and you see that now those signs will cancel out, right? The plus, the minus and minus will cancel out, and we get back everything is positive, right? The way we write it now. All right, good. So this is what we have, and you know how everything works from here, right? We are going to use elements which are subdomains I'm not going to write all the technical stuff about the union of elements, you know, with closure applied to them, giving us the total domain and all that, right? We don't need all of that here. Let's just look at the element subdomains, right? So we may work with quadrilaterals here, right, of that type. Okay, and just to fix ideas, let's suppose that we're working with bilinear quads. All right, so this would be omega E, right? We would have A equals 1, 2, 3, 4, which we know would be constructed from a mapping from a bi-unit domain, and we studied this process. Okay, we could have it constructed from a bi-unit domain, which is now expressed in terms of coordinates C1, C2. All right, and here our nodes are, we know exactly what these are, right? These are -1, -1, 1, -1, 1, 1, and -1, 1. Okay? Those are our nodes in the bi-unit domain. Okay? Now, we also remember that this mapping gives us a way to write out the geometry. Okay, so we know that the geometry in the physical domain is a function can be parameterized by our coordinates in this bi-unit domain. Okay, all right. So we may have this, or we may choose to be working with triangles, right? We may do that, or triangular elements. And in the case of triangular elements, I'll just do the very simplest of them. This is the one that we looked at in a previous segment. All right, that's omega E. Once again, we have nodes at the vertices, and I'm going to label them as A equals 1, 2, 3. We know that this can be constructed as a mapping from a unit domain, which we also express in terms of coordinates C1, C2, and in this setting we get that point is 0, 0, 1, 0, and 0, 1. Okay, and right, we also recall that in this setting our degrees of freedom here are labeled 1, 2, and 3. And that reminds me that I did not label the degrees of freedom on the bi-unit domain here. So let me call this 1, 2, 3, 4. Okay, but we know that already very well. Okay, and again we will get from here a mapping of the geometry as well, C1, C2. Okay. All right. So in this setting, we will get our basis functions, right? Right? There are two ways in which we would write our basis functions depending upon whether we were working with the bilinear quad or the linear triangle, right? In the case of the bilinear quad, right, we would get bilinear basis functions, right, bilinear polynomials, right. These would be written as NA parameterized by C1 and C2, all right, and we know what the formula for them is, right? I'm not going to rewrite it. We've written it a couple of times at least. Now these are the standard bilinears. We've also looked in one of the previous segments at the generalized Lagrange polynomial formula for this, right? So these are bilinear Lagrange polynomials, right? In this case, A runs over 1 to number of nodes in the element, and here number of nodes in the element is 4. Right? Okay. Or we would have linear polynomials, right, if we were working with the triangles, right? So the linear polynomials would again be written as NA, parameterized now by C1, C2, and remember the way that these things are written, often using area coordinates, we would include a C3, okay? And we remember that C3 is defined in the case of triangles as 1 minus C1 minus C2, right? And we saw this just recently in a segment. In this case, again, A goes from 1 to number of nodes in the element, and for the case that we're considering up here on this very slide, number of nodes in the element is equal to 3. All right, so this is what we have, and with this we go ahead and of course construct our finite dimensional functions, right? So we would go ahead and write UH over E is now sum over the number of nodes in the element, NA, right? I'm not going to write the parameters of NA because they could be different depending upon whether we are working with bilinear or linear polynomials, right? Whether we're working with bilinear quads or with linear triangles. So I'm just going to say it's NA times DAE, And for the weighting function, right, we have WH of E equals the same sort of expansion. Okay, right, we just need to remember that in the two cases, the number of nodes in the element could be different. All right,